And so I wanted to kind of mention that to everybody. All right, so this is November the 2nd, and so today what we are going to do, we are in finishing up chapter 10, so we're going to first do that. We're going to finish chapter 10, and so what we're going to do is we're going to review solving quadratic equations. We're going to go through a quick review of that, because those were things we were talking about before the exam, but those were not on your exam. So remember, the methods for solving quadratic equations are the factoring method, where you take two numbers and multiply them together to get 0. It means that one of the numbers has got to be 0. And we've talked about the square root method. And with the square root method, remember the equation has got to be in the form something squared equals a constant. Right? So both of those methods are what I would call special methods for solving quadratics, because they don't always work. Right? The first method, factoring method, requires that you be able to factor a quadratic, but not all quadratics are factorable. So if the factoring method does not always work. The square root method requires that the equation be in the form something squared equals a constant. So if the equation's not in the form something squared equals a constant, then you can't use the square root method. But the deal is that these methods are definitely the most efficient methods to use for solving quadratics. And so if they do work, then those are the methods of choice. That's what you want to try to use, is one of those two methods. And then we have two other methods, completing the square. And completing the square always works, first of all. So that's one thing, but not very efficient in most cases. So it is not necessarily the easiest method to use. And this is a way of forcing all quadratics to be solvable by the square root method. Its main use is not for solving quadratic equations. The main use for completing the square is that in graphing, first of all. So you're going to see it again in 13-14, graphing quadratics and graphing circles, things like that. Completing the square is important there. And it allows you to derive the quadratic formula. So you can actually create the quadratic formula using completing the square. And then that's the last method, the quadratic formula. And remember, the quadratic formula, we wrote this down, is a way of solving every quadratic. Right? It always works. Definitely not the most efficient way, but it always works. All right, and so we want to look at the quadratic formula also. And so we're going to go through kind of a review of these methods. I'm just going to work a problem or two out of each of these methods, kind of walk through that, and then we'll finish this part of the class with applications. So in other words, word problems. Very brief. I'm not going to spend a lot of time with that. We'll look at maybe one type of quadratic equation, but we're not going to spend a lot of time with that. That's just not something I wanted to deal with right now. And then we're going to have this huge shift in class, and we're going to go back and we're going to start talking about chapter 4. And in chapter 4, we're going to do an intro to graphing equations in two variables. And so that's chapter 4 in your book, and we are setting ourselves up gradually here to start talking about the idea of a function and functions, and that's kind of where we're going to sort of finish the semester. Is we'll have a couple of other things to do, but we'll finish by talking about functions, and that will be a good lead into college algebra, and which is basically a functions class. So college algebra is all about functions. And so you need to be pretty good at basic graphing and to start off and be a successful college algebra student. and you certainly need to know some things about functions, some basic things. And so this stuff that we're going to be talking about with graphing is going to be a lead-in to our discussion about functions, because when you deal with functions, you have to deal with equations and two variables. So it's just because that's just a characteristic of a function. So so that's kind of lays out what we're going to be doing this lecture. So let's get started. Let's just move right into this. So let's talk about quadratics and a review of quadratics, review of solving quadratics. And this is a good kind of overview of all the methods, so you can kind of see them all one last time. Remember, a quadratic equation is an equation. It doesn't have to be in this form, but it has to be something you can put in this form. And this is a degree 2 polynomial equation. Remember, it's got to be a second degree polynomial, so it must have this squared term. It does not have to have the other terms, but it has to have the squared term. All right, so first of all, factoring. So to look at a problem that you can factor, if we have this equation, 2x squared minus 5x minus 3 equals 0, right? Very, very classic, simple factoring problem. You must have the equation set equal to 0, remember, to use the factoring method. And you just factor this expression and you want it as a multiplication problem, right? That's the whole deal with the factoring method, is that you want a multiplication problem equal to 0. So I take 2x squared minus 5x minus 3 and I break it down as 2x plus 1 times x minus 3. That's how it factors. Don't forget, we haven't talked about this in a while, but don't forget to always check to make sure you get that middle term, the negative 5x, and so negative 6x on the outside and positive 1x on the inside gives me that negative 5x. And then set each factor equal to 0, and then solve each of those equations, and you're done, right? Pretty routine. So you get negative 1/2 and 3 as solutions. So that's a very typical factoring problem. That's a trinomial. Remember, it doesn't have to look like that. You could have an equation like this, 14x squared minus 21x equals 0. And in that case, there's a GCF, right? So you would take out the GCF. So this is a trinomial right here. Here you're taking out a GCF as your first step. Here I could take out a sub and x, and I'm left with 2x minus 3. And then set each factor equal to 0. One of the factors looks weird, but it's 7x equals 0. Shouldn't freak you out. You just divide both sides by 7, and you get x equals 0. And then over here you get 2x equals 3 and x equals 3/2. So solutions are 0 and 3/2 in this case. And then finally, you could have a difference of squares, right? The a squared minus b squared equals 0 factors is a plus b, a minus b. So these are the typical ways that you'd see factoring used to solve a quadratic. Trinomials, GCFs, difference of squares. Notice you don't come up with the difference of cubes or the sum of cubes when you're talking about quadratics, because cubes would require that it be a third degree equation, and so the sum and difference of cubes don't come up ever when you're solving quadratics, which is good, because I know most of you probably don't really like factoring using the sum and difference of cubes, just because it's kind of a pain to use the formula. So I'm just going to kind of squeeze these in. You get negative 3/2 and 3/2. All right, so when factoring works, it's not a bad method for solving a quadratic. You do have to have the equation set equal to 0, right? The equation must be set equal to 0 to use this method. All right, the next method that we've talked about this, so I'm just kind of going back and giving you an overview of all the methods. is the square root method. Square root method, remember, the equation has to be in this form. It has to be in the form something squared equals a constant. So if it's not in that form, then you have to make sure that you write it in that form first. So this equation, 2x plus 3 squared minus 36 equals 0, is not exactly in that form. Right? It's not in the form something squared equals a constant, but it is easy to put it in that form because all I have to do is add 36, right? And now it's in the form something squared equals a constant. And then I can go ahead and solve this using the square root method. Remember, the whole premise of this is take the square root of both sides of the equation. And the other thing to write here is don't forget, and this is the single most common mistake with the square root method, don't forget the plus or minus when you're talking about taking the square root of both sides of the equation. Because remember, there's both a positive and a negative solution to an equation like this. So you take the square root of both sides and you get 2x plus 3 equals plus or minus the square root of 36. Right? The square root of 2x plus 3 squared is just 2x plus 3. And you get plus or minus the square root of 36. All right, and then you're going to solve this for x. You simplify the radical if you can, which simplifies as plus or minus 6 in this case. And then solve. I would subtract 3 from both sides. Notice the plus or minus has to stay in front of the 6. It's addition and subtraction here. And then you have negative 3 plus or minus 6 over 2. Do not leave it like that. If you can simplify this, or in other words, do the arithmetic, you do it. So negative 3 plus 6 over 2 is 3 over 2. And negative 3 minus 6 over 2 is negative 9 over 2. And so those are my solutions in this case, 3 halves and negative 9 halves. All right, so that's a pretty routine problem for using the square root method. I want to look at one more problem before we finish the square root method. Let's see, let me kind of clean this up just a little bit. This is 3x plus 4 squared plus 8 equals 0. So again, you've got to get this in the form something squared equals a constant. So you subtract 8 from both sides. And now I'm ready to take the square root of both sides of the equation. So you get 3x plus 4. Let me erase that real quick. You get 3x plus 4 on this side of the equation equals plus or minus. Don't forget the plus or minus. And then this would be the square root of negative 8. Please don't forget that when you take the square root of a negative number, the square root of a negative here, that you get an imaginary solution, that this is imaginary, that you're going to have an I in the answer at the end. And so, you know, if you're working on WebAssign and WebAssign says find all the real solutions, then, you know, if the directions say that, if the directions say find all real solutions, then at this point in the problem, you would just say no real solutions because you've got the square root of a negative number. And so at this point, you would actually stop and say no real solutions. Sometimes on WebAssign, it's going to say that, find the real solutions to the equation. But if it just says find all the solutions to the equation, which is the way I'm going to ask this on the exam, and as a college algebra student, you're going to need to be prepared for imaginary solutions for sure, then I would want you to proceed on. You know, so if it says find all solutions, then you go ahead and finish the problem. So you get 3x plus 4 equals, okay, that plus or minus the square root of negative 8. the square root of negative 8, don't forget we simplify like this. It's the square root of negative 4 times the square root of 2. And then the square root of negative 4, that's the imaginary part. That is 2i. And then times the square root of 2. Remember that the square root of negative 1 is equal to I. Now, I think Anne-Marie mentioned this at the very beginning of our lecture today as far as the exam goes. But if you write that with the I at the end, it's not wrong. I'm just not going to write it that way because it's hard to see whether the I is underneath the radical or not. It's not, but when you write it that second way, it's kind of confusing. So I always put the I in front of the radical. I certainly would not ever penalize you for writing it that way. It's not wrong to write it the second way. Definitely not wrong to write it that way. In fact, WebAssign will sometimes write the problem that way. I'm just not going to do that in lecture at all because I want it to be really clear whether that I is underneath the radical or not. So in this case, then, what do I get here? I get plus or minus 2i times the square root of 2. All right, I've simplified the square root of negative 8. And then I subtract 4. Put the negative 4 at the beginning, please. Don't put it at the end so you're not confused as to whether it's underneath the radical. Keep the plus or minus in front of the 2i square root of 2. This is addition and subtraction. And then divide by 3. So you have negative 4 plus or minus 2i times the square root of 2, all divided by 3. And those are the, if you're talking about all solutions, those are the solutions to this particular equation. Negative 4 plus or minus 2i square root of 2 over 3. Right? And if the directions, again, it said find all the real solutions, then the answer would have been no solution at all. All right, so that's a quick rundown of the square root method. And we talked about that in the last lecture, but a quick rundown of the square root method. Completing the square. Completing the square, remember, is a way of forcing the square root method to be usable. So it forces the square root method. When I say it forces it, it takes an equation where you couldn't use the square root method, an equation that's not in the form something squared equals a constant, and you force it to be in that form. Now remember, I am only going to ask you very simple, very straightforward equations on this. So this would be a kind of example that we might look at for these completing the square. X squared minus 8x plus 10 equals 0. But notice that this is not factorable. There's no way to factor that. And it's also not in the form something squared equals a constant form. Right? So the first two methods don't work like we've got this one.
Are we going to have to work out if it's factorable and everything else before using completing the square, or are you going to tell us to use that method?
That's actually a really good question, and there's actually more to that question than you know. On this exam, Anne-Marie, I will definitely tell you, use this method, or I'll either say that, or I'll say use the method that you want to use, one or the other. Now, but there will definitely be some problems where I'll say use completing the square to solve this equation, right, specifically. That's one part to that question. The second part is, as a college algebra student, you are going to want to know whether the expression is factorable or not. And I'll actually show you a way you can tell whether it's factorable or not, because it's not something we've ever talked about this semester, but there is a way to decide whether it's, and I know for a lot of you, you probably look at a trinomial and you've probably asked yourself that question, how do I know whether it's factorable or not, or if I'm just not getting the right answer? And there is a way to find out, and it involves the quadratic formula, or at least part of the quadratic formula. So I'll show you how to figure that out in a little bit. So, but that's a good question. There's actually more to that question than you would know. So, all right. So we're going to use completing the square here and run down the steps for that. So the first thing you do is you move the constant to the other side of the equation. You always move the constant. And then remember, you leave a space, right? We want to leave an opening there. And then you fill in that opening always the same way. Well, negative 10 there. You always take the middle coefficient, the 8 in this case. It doesn't matter that it's positive 8 or negative 8 because we're going to be squaring, and so it's always going to be plus here. You take that middle coefficient and you multiply it by 1/2. It's always 1/2 that you multiply it by. And you get 4. And then you take that number and you square it, and you get 16. That is the number that you add to both sides of this equation. And remember, you got to add it to both sides. So I add 16 there, and I add 16 over here also. You have to add it to both sides. So, and add to both sides. Common to see students forget to add it to both sides and just add it to the left side instead. But remember, this is, we're trying not to change the solution to this equation, and so the only way to not change the solution is to do the same thing to both sides of the equation, right? All right, so this left side is factorable. It's guaranteed to be factorable if you've figured out that constant correctly. You have forced it to factor, and it's always a binomial square. It's always put the parentheses down, square it, and inside the parentheses you have the square root of the first term, the sine of the second term, and the square root of the third term. Always, 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 it's going to factor that pattern. And then on the other side of the equation, I have 6. And see, now what you've done is you've forced the square root method, because now the equation is in the form something squared equals a constant. It will always, always, always be in that form at that point. So now you take the square root of both sides of the equation. So you get x minus 4. The square root of x minus 4 squared is x minus 4. And over here, don't forget the plus or minus. And then you have plus or minus the square root of 6. Square root of 6 does not simplify, and so we can leave the radical alone. We just add 4 to both sides, and you get 4 plus or minus the square root of 6. And those are my two solutions. Nothing I can do to add those. One's a radical and one's not, and so I just leave it in that form. And so we've solved the equation 4 plus or minus the square root of 6 is our solution set. Now, completing the square can get much messier than what I've just done right here, and I'm going to steer clear of those kinds of problems. You're not going to have a problem that's messier than this on the exam. So this is a very typical test question right here, very similar to this problem. And I'm going to ask you, very typical test question, I am going to ask you one of these on the next exam, on exam 3. And it'll say, solve this quadratic by completing the square, or using completing the square. All right, so you just need to be prepared for a basic rundown of this particular method on the exam. All right, fourth method, kind of going through this, and we'll spend a little bit more time with this fourth method because we did not spend a lot of time with this in the last lecture. So the quadratic formula. If you took ax squared plus bx plus c equals 0, and you went through and completed the square, like I just did right here, there's a couple of extra steps you have to use, but if you completed the square on this equation, notice there's no numbers right in front of the x squared, the x and the constant. It's just at a, b, and c. Those are my numbers. If completing the square was used, on this equation, we would get this solution. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And so what we're saying when we write that down is we are saying that every quadratic equation, if you can figure out the a, b, and c values, they all have solutions that look like that one right there. They all have solutions that look like that. And so it's actually a formula. It's actually just a very traditional formula that you can use to solve any quadratic equation. So you literally just figure out what the a, b, and c values are, then you plug them into the formula, and then you do the arithmetic, and you get the solutions to the equation. It's that simple to use. Where I say it's that simple of a process. It's not necessarily simple to use, but it's at least that simple of a process. All right. So what we're going to do is work through some examples. And Anne-Marie, you asked a question about whether you could tell whether a quadratic was factorable or not. And we're going to use a part of this quadratic formula, and I'll mention that as we go through some problems, to show you how you can tell whether a quadratic is actually factorable or not. All right. Well, so let's look at some examples here. And so we've got r squared minus r minus 42 equals 0. So be prepared for the equation to have a variable that's not an x. You know, it could be any variable, doesn't matter. The deal is the equations must be in this general form for a quadratic, and once it's in that general form, you figure out the a, b, and c values, and then you can use the formula. So a is the coefficient of the squared term. It's the coefficient of the squared term. It's the number that's in front of it. And so that's a 1 in this problem. B is the coefficient of the linear term, the middle term. And so in this case, that negative r means this is negative 1. Excuse me. And then C is negative 42. It's the constant term. Please pay attention to the signs of these constants. That's very important in the formula. All right. So now we substitute into the formula. So x equals, now notice the formula starts out with the opposite of b. It says negative b. That's the opposite of b. Right? That's always the way to think of that, is the opposite of b. That's that constant right there. And so b in our problem here, oh, wait a minute. Notice I did make a mistake. I said x equals, but this would be r equals. Got to be careful there. And then the opposite of b, if b is negative 1, then the opposite of b is positive 1. So this is 1 plus or minus the square root of b squared. I always use parentheses in here, and I put the b value and I square it. Always use parentheses there. Minus 4 times a. I still just use parentheses as I'm substituting in, like so. And then over in the denominator you have 2 times a. Right, so we just literally just substitute everything into the formula. And then we solve this formula. Or not solve the formula, but we do the arithmetic. Anne-Marie.
Why do we change it from a negative to a positive?
Are you talking about the 1 at the beginning?
Yeah.
Look at the formula. The formula is x equals, and notice the way it's written. See, it says negative b.
Oh, and a negative makes a positive?
Yeah, and yes, that's correct. And I think the way to think about that negative b is don't say negative b. Instead say, remember that minus sign. Another way to look at that minus sign is it really means opposite of. So whenever you stick a minus sign in front of something, like if I put a minus and then a 3, that technically means the opposite of 3. Right? I put a minus sign in front of negative 5, and it technically means the opposite of negative 5. And so think of the negative sign as being opposite of. And so when I write negative b, I'm writing the opposite of b. So if b is negative 1, then the opposite of negative 1 is positive 1.
Okay.
Okay? Yeah, so that's a really common mistake to see students make. So you have to watch for that. All right, so I get 1 plus or minus the square root negative 1 squared, and you can see why you have to use parentheses there because it's a negative number. You square it and you get positive 1. I get students all the time who are telling me that's negative 1, but that's positive 1 because you're squaring negative 1 there. Minus 4 times a times c. Now notice you get 2 negatives in there because it's negative 4, positive 1, negative 42. So that ends up giving you a positive. So this is plus right here because of the two negatives. And this is 168. And then this is divided by 2. All right, you continue to do the arithmetic. You have to do everything underneath that radical. So you get the square root of 169 over 2, like that. And then you try to simplify the radical. And in this problem, notice that the 169 is a perfect square. It's 13 squared. So that we know the square root of 169 is 13. And so you get 1 plus or minus 13 over 2. And Anne-Marie asked about this before. This is the step right here that tells you whether the expression is factorable. When this number underneath the square root is a perfect square, like this one was right here, that means that the quadratic was factorable. It's just that number underneath the square root that tells you that. That number underneath the square root is the expression b squared minus 4ac, and that we actually give that a name in algebra. It's called the discriminant. The discriminant is the number underneath the radical, and it's b squared minus 4ac. It's just the piece underneath the radical. And this is one thing that the discriminant does for you. If the b squared minus 4ac is a perfect square, then the quadratic was factorable. It means there's a way to factor it. If b squared minus 4ac is not a perfect square, it's not factorable. So that's a way that you can actually decide at the beginning whether a quadratic is factorable or not, is to look at just the discriminant, b squared minus 4ac. So like in this problem, and I'll show you in a minute, r squared minus r minus 42 equals 0. That was a factorable expression. All right, so not a bad thing to know here. It's not necessarily critical for you to know that walking into college algebra, but your college algebra teacher is going to talk about the discriminant probably, and it would be nice for you to know what the discriminant means in that context, like that. Now, I have not finished our problem yet. This is 1 plus 13 over 2 and 1 minus 13 over 2. And so you get r to be 14 over 2 or 7, or negative 12 over 2 or negative 6. And so my solution set was 7 and negative 6 right there. By the way, that, remember that, so the discriminant on this problem was a perfect square. It meant that this quadratic was factorable. And I want you to see that, this definitely factored. R squared minus r minus 42 factored r minus 7 times r minus 6. I'm sorry, r plus 6. And so you set each factor equal to 0 at that point. And notice how factoring is much simpler to solve a quadratic. When it's factorable, that's much more efficient than the quadratic formula. That part in the red at the very top is the same thing as what I did in the black ink the rest of the way through there to solve this quadratic. So factoring is always much more efficient, certainly, but quadratic formula does always work, no question about that. All right, so let's continue this process here. Let's talk about a couple of more problems with the quadratic formula. And please don't hesitate to shout out and stop me as we go through this. So the next problem, we have 4v squared plus v minus 5 equals 0. Okay, so let's just practice the discriminant for a minute here. Does this factor? Is this factorable? Let's just practice that for a minute. So I would look at b squared minus 4ac in this problem. A is 4, b is 1 and c is negative 5. So if you use those values in b squared minus 4ac, which is the discriminant, you've got 1 squared minus 4 times negative 5. 4 times a times c. So you get 1 minus, or this is going to be plus again, and you get 4 times 4 is 16, times 5 is 80. You get 1 plus 80. Notice you get 81. It's a perfect square. So is it factorable? Yes. There is a way to factor this quadratic. Now that's not the way we're practicing this, but it is factorable, right? And you can see that this is not a too terribly difficult factoring problem. You have 4v here and v here, and you get 4v plus 5v minus 1 equals 0. So you set each factor equal to 0, and you solve, and you get negative 5/4 and positive 1. Now that's not what we're practicing here, but I did want to run through that. You could have factored this to solve the equation. So using the quadratic formula, which is what we're practicing, we get x equals, or not, I'm sorry, not x equals, v equals, because v is the variable in this problem, v equals the opposite of b. So b was 1, so the opposite of b is negative 1, plus or minus the square root of b squared. Oh, and by the way, b squared minus 4ac, we've already done. You know, if you want to think about that, we calculated it off to the side and got 81. So if you wanted to, you could take advantage of the fact that you've already done that. Over 2 times 4, 2 times a. So v would be negative 1 plus or minus, and we know that that's the square root of 81 over 8. So you get negative 1 plus or minus 9 over 8. And so that gives you two solutions, negative 1 plus 9 over 8 and negative 1 minus 9 over 8. Negative 1 plus 9 over 8 is 8 over 8, or 1. And negative 1 minus 9 is negative 10 over 8, or negative 5/4. Sure enough, you get the same solutions, but definitely harder to do the quadratic formula, or a little bit messier, I guess I should say. So, all right, so another good quadratic formula problem done. Next problem I want to look at. Let's look at this equation. We have 5z times z minus 2 equals 3. 5z times z minus 2 equals 3. Now, if you're going to solve using the quadratic formula, the equation must be in the form ax squared plus bx plus c equals 0 in order to use the formula. And so if it's not in that form, then you've got to put it in that form. And so that's what I've got to do in this problem. I've got to put it in that form. So put in general form. All right, that form right there is what we need. So you multiply through by 5z. So you have 5z squared minus 10z equals 3. And then you subtract 3. And you've got the equation in the right form here. I want you to notice also that this is not factorable. If you look at the discriminant, b squared minus 4ac in our problem, a is negative 10. No, hardly. A is 5. That's better. B is negative 10, and C is negative 3. So you get negative 10 squared minus 4 times 5 times negative 3. So you get 100. And then 4 times 5 is 20, times 3 is 60. You have two negatives in there, so it's plus, and you get 160. 160 is not a perfect square. And so this quadratic is not factorable. There's no way you could use factoring to solve it. So you have to use some method like completing the square or the quadratic formula to solve the equation. So we get z equals, and we get the opposite of b. So b is -10, so the opposite of b is +10. Times the square root of b squared. So this is -10 squared. Use parentheses. -4 times 5. Use parentheses here to keep these signs straight. All divided by 2a, all divided by 2 times 5. So you get z equals 10 plus or minus the square root of 100 plus 60. And we've already done the discriminant off to the side, so you could have taken advantage of that. Please do not cancel the 10s here. Can't cancel these 10s because there's addition and subtraction in the numerator. So don't cancel the 10s right there, right? Not allowed to do that. So instead, we've got 10 plus or minus the square root of 160 over 10. And then we simplify the square root of 160. And now the square root of 160, it's kind of big, but it's not too bad. You can break it up as the square root of 16 times the square root of 10. And so that's 4 times the square root of 10. Charlotte?
Sorry, my screen went black and I had to press a button.
Okay. You didn't really have a question then, I guess.
No, I'm good.
Are you sure?
I'm sure.
Okay. So you have 10 plus or minus 4 square root of 10 over 10. And now you can cancel because there's a common 2. There's a common 2 in all 3 terms. The key there is the word all. It's got to be in all of them. And so there's a common 2 in all of these. And so I can cancel it out. But it's got to be in all of them. And so you get z equals 5 plus or minus 2 square root of 10 over 5. And those are the solutions to this quadratic. Like that. All right, so hopefully we are good there. Hopefully there's no questions on that problem. And so now as far as, let's see, as far as word problems, we're going to do one word problem here. I'm going to very limited as far as word problems go on these kinds of problems. All I'm going to do is look at some geometric kind of problems and really just having to do with rectangles and maybe triangles, and that's it. And so I'm going to work a triangle problem right here. And so, by the way, in your book, this is on page 1219 of your book, and this is problem number 290 in your book. And in this case, you have a triangular bookcase. The height is, I'm just going to write down the important information. The height is 6 inches less than twice the width. The area of the back of the case, so the area of the case is 70 square inches. 70 square inches. Find the height and the width of the case. All right, so that's the important information right there. So you're talking about, I know it's a triangular bookcase. I don't think I've ever seen a triangular bookcase before, but that's what it says. So you have a triangular bookcase like this, and you've got, this is the width down here, sometimes called the base of the triangle, and this is the height right here. And that's the height like that. And now, if you remember, I don't know if you remember the formula, but the formula for the area of a triangle is the area is 1/2 the base times the height. It's 1/2 the base times the height. And so in our problem here, we should let the width be x, and then notice that this sentence right here, height is 6 less than twice the width. So we've let the width be x, and so the height is 6 less. We take 6 away from twice the width. So the height is 2x minus 6. So we have here that the width, or the base, is x, and the height is 2x minus 6. And then we also know the area is 70. So you take all of that information and you substitute it into this equation right here. All right, so when we do that, we've got 70 equals 1/2 the base, and remember base and height and width mean the same thing. So 1/2 times x times the height, which is 2x minus 6. And so notice what you end up with here is a quadratic equation, because when you multiply this out, you're going to get an x squared in there. And so this is a quadratic equation that we would want to solve, that we're going to solve to answer the question in this problem. Now, what do you do with that 1/2 would be a good question to ask at this point. And what I would do before I do anything else is I would get rid of the 1/2. Because you don't really want a fraction in there if you can help it. And so what I would do is I would simply multiply both sides of the equation by 2. If you do that, right, so notice I'm just multiplying both sides of the equation by 2. That would clear the fractions out because, on the left side you get 140, but on the right side these would divide out, and you'd just be left with x times 2x minus 6. Right, and so I would get rid of the 1/2 there, and so multiplying both sides by 2, multiply both sides by 2 is the way to go there, to get rid of the 1/2 in that formula. So now this is a quadratic, and it's not in our general form, so I would first multiply this out. And then remember, you need 0 on one side. Since the x squared is on the right side, I would subtract 140 from both sides of the equation. And that way I have 0 on the left side. It doesn't matter. It equals 2x squared minus 6x minus 140. All right, so now you've got the equation in a nice form. It doesn't matter what method you use at this point. Regardless of what method you use, there's a common factor of 2. Take out that 2 to make the numbers smaller. Whether you're using the quadratic formula, whatever method you're using, or factoring, won't matter here. You're making your life easier by taking out the GCF. All right, so I took out the GCF, which was 2. Oh, and so technically I have this 2 sitting in front of here. And then I would just divide both sides by 2. If you divide both sides by 2 at this point, you're taking 0 and dividing it by 2, and you're taking this and dividing it by 2. And you just get 0 equals x squared minus 3x minus 70. You want to get rid of that thing, that 2 at the beginning, and so just dividing both sides by 2 makes it go away. And so now you don't have to worry about that 2 anymore, and now you can proceed on with the problem. Now, this quadratic is factorable, because you can use 10 and 7 to do that. I'm going to use the quadratic formula just to practice the quadratic formula one more time. So you would not have to use the quadratic formula here, but I'm going to use it just to practice it. So you have A is 1, B is -3, and C is -70. So when you substitute, you get x equals opposite of b, which would be 3 plus or minus the square root of b squared. So this is -3 squared minus 4 times a times c, all divided by 2 times 1, like that. So you get x equals 3 plus or minus the square root of 9 plus 280 over 2. And so that gives me 3 plus or minus the square root of 289 over 2. And believe it or not, 289 is a perfect square. That is 17 squared. And so you get x equals 3 plus or minus 17 over 2. Now that gives you 3 plus 17 over 2. We have to kind of squeeze this in over here. And that gives you 10. 20 over 2 are 10. And you get 3 minus 17 over 2, which is -14 over 2, or -7. Now remember what x represented in this problem. X represented the width. And because it represents the width, it's got to be positive. And so I would throw out -7 in this case, because x could not be a negative number. So I'm going to put this at the very top, kind of in a different color so it kind of stands out. So the width, we said at the beginning of the problem, was x, but we found x to be 10. Right? And so, right, because we've thrown out -7. And then the height is 2x minus 6. And so x is 10, so this would be 2 times 10 minus 6, or 20 minus 6, or 14. And so those are the dimensions that we're looking for in our problem. That's the solution to the problem. Right, so we have found the height and the width. Remember, the height and the width were what we were being asked to find. I'm going to circle that right here. And I found them up here, right, after we solved the equation. In a geometry problem, typically when you get a negative solution to an equation, you're going to throw out that solution. Right, so just to kind of let you know that. All right, so now that finishes what we are doing. This finishes what we are going to do with Chapter 10. All right, and in Chapter 10, just like in some of the previous chapters, we've been solving equations. So far this semester, what we've done is we've looked at equations using one variable. Like all these equations I've just been talking about, if you look at every equation I've solved, this word problem, this quadratic right here, this quadratic right here, all of the problems we've talked about today and previously this semester have all been equations that involve one variable only. And so when we go back to Chapter 4, we are going to make the transition to equations in two variables. Chapter 4 is all about equations in two variables. So what I want to do here to finish class, we're going to take about 10 or 15 minutes to get a good start into what we're doing with the equations in two variables, and I want to talk about some basic things here. So look, this is an equation in one variable right here, and I'm going to do a simple one. Equation in one variable might be something like this: 2x minus 5 equals 7, something like that. So what do? We add 5. We divide by 2. We get x equals 6. That's the solution to this equation. That's an equation in one variable. When you make the jump to equations in two variables, a lot of things change. And you got to do things differently. So this is an equation in two variables, 2x plus y equals, let's say, 7. So it looks somewhat similar to the problem we just did, but instead of that 5, we got that negative 5, we've got a y. So you have 2x plus y equals 7. Solutions to this equation, this kind of equation, first of all, look different, right? Solutions are no longer just numbers like we have, like the 6 in the first one. The solutions are ordered pairs. So, for example, in our problem, the ordered pair 3, 1, right? Ordered pairs where the first coordinate is the x-coordinate and the second coordinate is the y-coordinate. So the ordered pair 3, 1 is a solution because 2 times 3 plus 1 is equal to 7. Right? So 3, 1 is a solution to this equation. Let's see, negative 2, 10 is not a solution because if you do 2 times negative 2 plus 10, right, I'm just substituting the x in for x and the y in for y, or the first coordinate in for x and the second coordinate in for y. Maybe that's a better way to say it. So you have 2 times negative 2 plus 10 equals 7, but that is not a true statement because you get 6 equals 7. So that's not a solution. All right, so you get a false statement at the end. 6 is not equal to 7. All right, and so the solutions look different, first of all, for an equation in two variables. Equation in one variable, you just get a number, 6. For an equation in two variables, you get an ordered pair like 3, 1. So that's one big difference between equations in one variable and equations in two variables. Another big difference is typically the number of solutions you get. This equation in one variable has just one solution. Our equation in two variables, 2x plus y equals 7, 2x plus y equals, 2x plus y equals 7, has an infinite number of solutions. Three, 1 was an example of a solution, but it's not the only solution. 0, 7, if you check 0, 7, 0, 7 is a solution to that equation. 2, 3 is a solution to that equation. Negative 1, 9 is the solution to that equation. 1/2, 6 is the solution to that equation. 0, 7, oh, I already did 0, 7. 7/2, 0 is the solution to that equation. Right? This goes on forever. You can check all 6 of those ordered pairs that I just put in there. But every one of those would make that equation true, like 1/2, 6, for example. Right? Substitute that into the equation 2x plus y. 2x plus y equals 7. You get 2 times 1/2 plus 6 equals 7. You get 1 plus 6 equals 7. You get 7 equals 7. Right? These are all solutions to that equation, and I could write these down for the rest of my life, and I would not be able to write them all down. Right? There's an infinite number of solutions to this simple linear equation in two variables. So to show someone the solutions to an equation like 2x plus y equals 7, I can't just list all these solutions. I can't list these solutions because there are too many of them. It has literally an infinite number of solutions. And so because it is an infinite number of solutions and you can't list them, if you were going to show somebody the solution set to this equation, then what do? So we draw a picture of the solution set instead. And that idea is drawing a picture of the solution set. Draw a picture of the solution set right there. That's when you talk about graphing an equation, that's what you're talking about doing. When you're talking about graphing an equation in the plane, you're really just drawing a picture of the solution set to that equation. And I think a lot of students kind of tend to lose sight of the fact that that's what they're doing, is they're actually drawing a picture of the solution set to that equation. So for example, 2x plus y equals 7. A common way to write the solutions down and to calculate solutions for an equation like this would be to make a t-table. This is a basic method for sketching graphs. It is not necessarily the best method for sketching graphs. So like if you look at my college algebra notes, you'll see that sometimes I make a little t-table to sketch a graph, but very quickly we get away from t-tables and try to find other methods for solving or for finding solutions to an equation if we're trying to graph it, because plotting points is frequently not a good way to solve it because sometimes you have to plot too many points. But if you're going to use a t-table like I'm doing here, a nice way to do this is to kind of fill in the x's with some typical values, like maybe -2, -1, 0, 1, and 2 wouldn't be a bad group of points for this equation right here. And so what you do literally is you just substitute those x values in to the equation and then find the corresponding y value, right? So like I've got -4 plus y equals 7, so y is 11. So I get -2, 11 as an ordered pair that's a solution to that equation. 2 times -1 plus y equals 7, right? I use -1 there. So you get -2 plus y equals 7, or y is equal to 9. So I get 9. And I could keep on going like this. So 2 times 0 plus y equals 7. That's easy. That's just y equals 7. I use 1. 2 times 1 plus y equals 7. So I get y equals 5. Notice that as the x values get bigger by 1, the y values are decreasing by 2, it appears, every time. And that's actually true in this equation. And that's something we're going to take advantage of later. Not at this point, but we will eventually. 2 times 2 plus y equals 7 is 4 plus y equals 7. Y is equal to 3. So you get a nice little group of points there that you could actually sketch the graph of this equation. We sketch the graph on a coordinate system. Like this, remember that this is the x-axis and this is the y-axis. I'm definitely assuming that you've had some experience with the x-axis and the y-axis in plotting points. I'm definitely not assuming that this is the first time you've ever seen this. So this is kind of an introduction to graphing, but it's something that I'm expecting that you have encountered before. First of all, in our introductory algebra class, you certainly would have seen graphing in the plane like this. So -2, 11. So let's see, 1, 2, 3, 4, 5. There's 5 right there. 6, 7, 8, 9, 10. There's 10 right there. So -2, 11 is way up here. And -1, 9 is here. And 0, 7 is here. And 1, 5 is here. And 2, 3 is right here. And notice that it appears clearly that all of the solutions to this particular equation lie on a line. And that is exactly true here. This is definitely, the graph of this is definitely a line. And when I draw that line like that, I'm drawing a picture of the solution set to 2x plus y equals 7. Okay? And so, first of all, one thing to point out here is that this equation we just talked about is an example of a linear equation in two variables. This is a linear equation in two variables. The x is raised to the first power, the y is raised to the first power. And because it's a linear equation in two variables, the graph is always going to be a line. The graph is always a line. That's why they're called linear equations. All linear equations have graphs that are lines. And that's what we want to talk about a little bit here at the beginning, is simply looking at some equations in two variables and creating some solution sets for these and actually sketching their graphs. All right, so let's look at 2x minus 3y equals 6. 2x minus 3y equals 6. So this is our example right here. So we're going to make a little table of values here and actually calculate or sketch the graph based on these calculated values from our t-table. So we're going to make a t-table out. We're going to actually use the values -2, -1, 0, 1, and 2 like this and put those in for x. Typically that's what we're going to do, is use x values here. There may be occasions where using a y value makes more sense, and you'll kind of get the idea as you go through this. All right, so substituting, let's see, so substituting -2 in for x, you have 2 times -2 minus 3y equals 6. So you have -4 minus 3y equals 6. Add 4, you get -3y equals 10. Y is -10/3. One thing is, if you use a t-table like this and just use values like -2, -1, 0, 1, and 2, you sometimes are going to get fractions. There's ways to deal with that and get points that are not fractions, but if you just use values like I'm doing here, then you're going to get fractions for solutions sometimes. So we use -1 for x. So you get -2 minus 3y equals 6. -3y is equal to 8. Y is -8/3. So you have -8/3 right there. Use 0. That one is always easier to use. And so you get 2 times 0 minus 3y equals 6. So you get -3y equals 6, or y equals -2. So you get 0, -2. Next one is 1. You get 2 times 1 minus 3y equals 6. So you have -3y equal, you have 2 minus 3y equals 6. -3y is equal to 4. Y is -4/3. And by the way, notice that the y values now seem to be increasing by 2/3 every time. As you go from point to point, here, these x and y values, the y values seem to be increasing by 2/3 each time, which is exactly true.
Why is it -4/3?
Let's see. So I substituted in x equals, here's the problem right here. I substituted in 1. So I get 2 minus 3y equals 6. So I subtract 2. I get -3y equals 4. Yep. So y is -4/3. Right, because I had the -3y.
Divide the negative, it doesn't turn to a positive.
But I'm dividing a positive by a negative, right?
We're going the other way. Sorry.
Yep. No problem. Definitely. I'm always thrilled when somebody stops me and has a question, because sometimes I feel like I'm not sure whether you guys are there or not. So I always the downside to teaching an online class definitely is I can't see your faces. I don't sometimes lose sight of whether you guys are following what I'm doing or not. But I can see your faces. A lot of times I can get an idea whether you're actually following what I'm doing. All right, so notice you get a lot of fractions in this problem. So when you graph this, you do you estimate those as best you can. So like, negative 10 thirds is negative 3 1/3. You're dividing 10 by 3, remember. This is negative 8 thirds is negative 2 2/3. And then negative 4 thirds is negative 1 1/3. All right, so use those to help you plot these points correctly. So you have negative 2 and negative 3 1/3. Down here, I'm going to put this in a different color. Negative 1, negative 2 2/3. Negative 1 and negative 2 2/3, about right here. 0, negative 2, here. 1, negative 4 thirds. It's 1 and negative 1 1/3. It's about right here. And then finally 2, negative 2 thirds is right in here. And so here's our line. Right, and so we get a decent sketch of the line right there. Now, one thing, since the graph is a line, if you know that the graph is a line, you really only need 2 points to sketch the graph. Now, I've been using more points here just to start out with, just to kind of get you thinking about lines again. But if you think about it, the ordered pairs where the arithmetic was the easiest is when you use 0 for x or y. And so if you think about that for a second, that would be a way definitely to streamline this process significantly, is to use 0 for x and use 0 for y in your t-table. So like if we had 5x plus 3y equals negative 6, let's say, I can make a t-table, but in the t-table, I could simply use 2 points and put 0 in for x for one of them and put 0 in for y for the other one. When I do that, I'm really making the arithmetic much simpler. Right? You get 5 times 0 plus 3y equals negative 6. So you get 3y equals negative 6, or y equals negative 2. Most of you can probably do that arithmetic in your head. And then when you use 0 for y, so now I'm substituting a y value in. And that's 0 right there. And so you get 5x equals negative 6, or x is negative 6/5, which is negative 1 1/5. And so you get these 2 points. If the graph is a line, and it's a linear equation, so we know its graph is a line, really, we could get by with just those 2 points. 0, negative 2 is here, and negative 6/5 is about right here. And so there's our line. Looks like that. 0, negative 2, when we put 0 in for x, we got negative 2 for y, that's this point right here. And notice that's the place where the graph crosses the y-axis. That is called the y-intercept for the graph. And negative 6/5, 0, which is this point right here, is on the x-axis. This is called the x-intercept. Graphing lines using the intercepts is frequently an easy way to graph the equation. For one thing, it makes the arithmetic easy, but using intercepts to graph, all you're doing is making a t-table where you're putting 0 in for x and 0 in for y. When you put 0 in for x, you're talking about the y-intercept. And when you're putting 0 in for y, you're talking about the x-intercept, like that. All right, so we'll certainly talk more about that next time and talk about the intercepts. Your textbook homework. So this gives us a good start on graphing lines, and we're gonna, next time it's gonna be all about lines and graphing lines, basically. So, all right, so your textbook homework, this is page 421 of your book, problems 21 through 47 odd. This is on graphing lines. graphing lines. And then out of chapter 10, I think the textbook homework there that would be good to look at would simply be out of the review exercises. And those are on page 1217. This is chapter 10 stuff. This is solving quadratic equations. And really, I would think problems 213 through 277, every other odd would probably be okay. Every other odd, and that would give you some good practice. And then number 289, which is a word problem, which would be a good one to work. And like I said, I'm not going to be doing a lot with word problems, but that word problem's a lot like the one we did in class today. So before you leave, I do want to point out that the spring schedule went visible yesterday, I believe. So you are now able to go in and look at the spring schedule. And so you ought to start thinking about how your spring is looking. I do want to point out that I am teaching 2 sections of online college algebra in the spring. And so you guys are intermediate algebra students, all you who are with me live today, and then those of you who are watching the video later. And so if you think this has been a good format for you for an online class, my college algebra class in the spring is going to be very similar. Only some minimal changes to the format, the way I'm going to do things in the spring. And so, please think about enrolling in college algebra, one of my online sections. And am I recruiting people? Yes, I definitely am recruiting people. I'm not ashamed to say that. So if you're a good student, if you like this format, I'd love for you to carry over and sign up for college algebra in the spring.